Some interesting stuff today. Your last assignment's due on Friday. For the final exam next week, less than a week away, I'll provide the equation packet and the geometric properties that are relating things like area, depth, wetted perimeter, and so on. That's table 10.1. And you should also bring your laptop with you because you'll have some sort of problem where you need to use it, whether it's water surface profile related, like gradually varying flow, maybe direct step method, standard step method. It would be reasonable to expect one at least of those types of problems. But then looking further back into the semester, we've had things like 3 reservoirs, Hardy Cross. There's just been a lot of different things you've used spreadsheets for. The exam's comprehensive. A disproportionate number of the points are going to come from the more recent material that you haven't been yet tested on. And I'm hoping to make the problems in general a little bit smaller in length so that I can give you more of them, and then you have like a greater number of questions. So if there's one thing that you forget, it doesn't give you like quite as big a penalty as if there's only 5 questions and you totally blow it on one of them, that's 20%. But if there are 15 questions and you blow one of them, then that's a much smaller fraction of your overall grade. So does anybody have any questions related to the announcements? All right, so we're going to continue talking about the unique case of open channel flow through circular conduits. And that's what we have for both storm sewers and sanitary sewers. And remember how we talked about sewers are rarely flowing full, and so we have this unique issue of measuring the angle that the water surface makes with the center of the pipe in radians, and we assign that variable theta. And so if you know the angle, then from that you could determine the depth, you could calculate the area, wetted perimeter, the top width, and so on. If you don't know the angle, but you do know the depth, then obviously that would be the only unknown. You can solve for theta with the given depth. So Manning's equation, when we put in all of these unique geometric parameters for like a partly full pipe, Manning's equation, now this is in SI units, translates into this, where everything's in terms of theta. So we're going to work 2 examples today. One where we know the depth, and we're trying to find out what's the flow rate through the pipe for a certain depth. And then the other example we're going to work is the depth is not known, and that's what we have to find out. So let's look at that first example. And something you need to know about water flowing through a pipe that isn't full is that the end value is different compared to if the pipe was full. So think about end value characterizes roughness, basically. It's how we account for energy loss due to pipe friction. And so think about if the pipe is, if the water depth in the pipe is very shallow, let's say it's just very, very shallow, then the ratio of the cross-sectional area to the wetted perimeter where the friction is applied is much different than if you had a pipe like this and it's mostly full. So if it's mostly full, you've got a huge cross-sectional area compared to not that much of a different wetted perimeter. I mean, the wetted perimeter of this one's probably double, but the flow area is probably 6 or 7 times as great. So as a result of that, we have to correct for the end value if the pipe isn't full. And so that's part of what is being illustrated in this nomograph. Look at the top axis here. The top axis is saying the ratio of n to n full. So what it means is if on the vertical axis over here, if you look, it's the ratio of the depth of water to the diameter of the pipe. So for example, if the water depth is half the diameter of the pipe, so here, the ratio of y, the depth of the water to the diameter of the pipe, If it was 0.5, then what you do is you'd follow this over to the point of intersection with the Manning's N curve, and then you'd go up. And so what that's showing is that the ratio of N to N full is 1.25. So that the N, if the pipe is 50% full, would be 1.25 times the N when it is full. So let's say if it was a concrete pipe, a typical N value would be 0.013. So if you multiply 0.013 by 1.25, then that tells you that the N value for a concrete pipe that's half full would be 0.01625. So the roughness value, the effective roughness, is higher if the water isn't all the way in the pipe. So that's one of the things that's being illustrated in this figure. Does everybody understand that idea of why the N value would be relatively higher if the pipe isn't all the way full? Okay. Another thing that this figure is showing is the ratio of the flow rate compared to if the pipe was full. So one of our techniques for solving problems like this is just find the flow rate through the pipe if it was full, and then multiply it by this ratio. So let's say, for example, we've got the same like 50% full case. If the depth y was 0.5 of the diameter of the pipe. So if we follow this over and intersect this curve, which is the ratio of Q to Q full, if you follow it down, what it's saying is that it's about 42% of the flow rate. So when the pipe is half full, you don't get half of the flow rate. You only get 42% of the flow rate. So it's a nonlinear response. You know, if the pipe is 10% full, it's not 10% of the flow rate because the ratio of the wetted perimeter to the area is so far in the extreme. So that's why this is not a straight line. This is a nonlinear curve because as you get deeper, progressively deeper, you're getting more flow area with less wetted perimeter. So you follow the Manning's curve up to the top, and then the ratios for flow rate and velocity go down here to the bottom. Now there's one thing that's very, very strange about this curve. I want to give you a moment. See if you can figure it out. Follow the Q to Q full curve. There's something unexpected on it. Does anybody see what's very strange about the Q to Q full? What is it?
If it's almost all the way full, it's greater.
Exactly. Yes, so look at when it's almost full. So 80% full, 90% full, 95% full. So what he noticed is when the pipe is like 95% full, the capacity is higher than if it's all the way full. So let's take this all the way up to 95% full. Why would it be that if it's 95% full, you're actually going to be able to carry more flow than if it goes that last little bit to the top? Friction? Say more.
Because you're not getting a lot of cross-sectional area to compensate for that, lots of friction.
All right, exactly right. So when it's 95% full, if you take it up the rest of the way, you're just getting a little bit of flow area, but you're getting a lot of wetted perimeter. And so you're better off not getting that extra flow area and avoiding the additional friction, because think about it, when the water's not quite touching the top, no resistance on that entire length. But as soon as it goes to the top, it's about the same length, but now it has resistance. So it's kind of an interesting thing. This figure's capturing the fact that you actually have better flow performance when it's almost full than you do when it's all the way full. Okay, so let's work an example. Let's say that we know the depth of flow. We have a pipe that is 24 inches in diameter. Okay, so I guess first things first, we're in traditional units. You'll see that I've given you the Manning's equation with the 1.49 prefix in the front there. Okay, so I think I just got this on my shirt, this marker. So the depth is 9 inches. Let's maybe change this figure a little bit. So our depth of flow is 9 inches, and the diameter is 24 inches. Okay, I'd like you to solve this 2 different ways. First of all, we're going to do it using the nomograph. So find out what would be the flow rate if the pipe was all the way full. So find Q full, and then use the nomograph, the ratio of Q to Q full for whatever the depth to diameter ratio is. Okay, so then part 2, things are going to get a little more complicated. We'll do it by the angle method, where we're going to find what is theta for the conditions that are described. So see this equation that's in red here? That'll allow us to find theta. And there's a function on your calculator called the arc cosine. It's just the inverse of the cosine. Does the Casio calculator have arc cosine? All right. So we'll want to find the angle and then the area, wetted perimeter, and then you put those into this, and then you still have to make a nomograph correction. You have to correct for the ratio of n to n full. Okay, so 2 different ways, the nomograph method and the angle method. I'll be writing on the whiteboard in case you want to check as you go, but let's take some time to get this figured out. Okay, so if the pipe was full, the area would be 3.14 square feet. If the pipe was full, the wetted perimeter would be 6.28 feet. And so we put those 2 parameters into Manning's equation, and we don't change the n value if the pipe is full. It's just the given n value of 0.013. So if the pipe was full, it would be 16.04 cubic feet per second. And now we go to this figure and we find out what's the ratio of depth to diameter. So it's 0.375. So we have to be pretty careful here on the figure. You know, this is 0.2, this is 0.4, so that makes this 0.3. And then 0.375 is 3/4 of the way between 0.3 and 0.4. So we maybe kind of mark where the midpoint is, so halfway, and then another halfway would get us to the 0.375. And then reflect that down off of the curve for flow rate to Q full. And I thought that looked like 0.24 when I looked at it before. Now it looks like 0.23 to me as I'm looking at it. But, you know, if I go with my original assessment of 0.24, what we'll do is multiply that 0.24 by the full flow rate of 16.04. And so that says that if the pipe was flowing at 9 inches, the flow rate that we expect to see is 3.85 cubic feet per second. So 3.85 CFS. If it's 9 inches, laid out on a 0.5% slope, concrete pipe that would be 0.013 when it's full. So does everybody understand this first method of using the nomograph when we assume, like we find out if it was full and then we correct? Okay, the next part is a little bit more creative, maybe indirect, tricky somehow, the angle method. So we want to use that formula to find out what is the angle based on the depth. So let me just pull that up here. So this is the formula that the angle in radians is 2 times the arc cosine, and what's in the brackets here is 1 minus 2 times the depth divided by the diameter. So 1 minus 2 times 9 divided by 24. The inside of that parentheses ends up being 0.25, because it's 1 minus basically 0.75. So what's left over is 0.25. And make sure your calculator's in radians mode, because if it's in degrees mode, you're not going to get this same value that we need. But if you've got everything set up correctly on your calculator, you should get 0.2636, no, 2.636 radians is the angle. And that kind of makes sense. Like, always compare this to reality and what's reasonable. So pi radians is half full. So this is going to be less than pi radians because it's not yet half full. It's only about, 37% full. So, I mean, just from the perspective of reasonableness, this angle, I think, does match our expectations. So we found theta, and when we know theta, we can use this to find the area and the wetted perimeter, and then we're going to use that to find the, we're going to use the figure to find out the end-to-end full that we need, and then you can put all of that into Manning's equation. So let me pause again for a moment. Now that we've all agreed that the theta here, the angle that we're looking for is 2.636, calculate the area, wetted perimeter, and then find out what's the new n value that we should be using. If it is, this amount full. If it's 37.5% full, we go over here and then up to find the ratio of n to n value. So let me pause the recording, maximize this again so you can get a better look at the figure. Okay, so if we do it this other way, by finding out what the angle is, and then using that to find the area, wetted perimeter, and the corrected n value, then you can see the result. The flow rate is 3.78 cubic feet per second. So the first method, we got it was 3.85 cubic feet per second. This one, 3.78. The difference is just simply how we are reading numbers off of that nomograph. We're not going to be 100% accurate and precise in the way that we read values off the nomograph, but in reality, this is pretty close. Those two flow rates are different by only 2%. The difference between 3.85 and 3.78 is about 1.9%. So we effectively get the same answer either way. One method, we just found the flow rate if it was full and then corrected. That's maybe the easier of the two methods. The other, though, if we needed to know the angle, we could calculate that. And then we still have to use the nomograph to calculate for the effective n value when the pipe isn't all the way full. So does anybody have questions about either of these two approaches? All right. So this is an example where we had a known depth, and we're just finding out what's the flow rate for this depth. So if we went into the field and we knew the slope of the pipe and we knew the diameter of the pipe and we stuck a ruler down into the sewer and we measured the depth of flow was 9 inches, throw the ruler away and then start our calculations, because here we wanted to find out what is the flow rate. Now, there's something that you need to know about that's kind of at the intersection of hydraulics and environmental engineering, and that is that there is a dangerous, corrosive, poisonous gas that can form when wastewater decomposes in the absence of oxygen. And when there is sulfur in wastewater that is anoxic, then the bacteria that break down BOD in the absence of oxygen can transform the sulfur into hydrogen sulfide gas. And it's very dangerous. As low as 300 parts per million could potentially kill a person if the exposure duration was long enough. Higher concentrations are dangerous in shorter time periods. And it's also corrosive because hydrogen sulfide is oxidized to sulfuric acid. And so it causes pitting of concrete pipes. It can cause rust, like premature rusting and oxidation of metal in wastewater treatment plants if hydrogen sulfide is formed. And so there are things that hydraulic designers can do to try and prevent anaerobic conditions and hydrogen sulfide from forming. Like, for example, if your pipe is too big, like if you've exaggerated your demand estimation and the pipe is too big, then what happens is that most of the time the water's going to flow very shallow in that pipe. And so usually we think of like oversized pipes as being good because we're providing plenty of capacity. But if the pipe is so big that the depth is shallow, then you've got a lot of wetted perimeter and a slow velocity. And slow liquid velocities don't have very much mixing and aeration of the liquid. And so then there would be a greater risk of hydrogen sulfide forming at the bottom of the pipe as things settle down, cause like kind of clogging and collection in the bottom of the pipe. And so one of the risks of having an oversized pipe is that it's not self-cleansing. Self-cleansing is the idea that if you maintain a high enough velocity that the solid waste, paper, debris won't settle to the bottom of the pipe and you're less likely to have hydrogen sulfide forming. So one of the ways we can estimate the risk of hydrogen sulfide formation is by calculating this sulfide potential, Z. It's just an empirical equation that's been developed through observation, and it takes into account an effective biochemical oxygen demand, which is a representation of the strength of the wastewater. You know, if the wastewater has a lot of pollutants in it that are going to be attractive to bacteria that form hydrogen sulfide, then that increases your sulfide potential. And the bacteria are more active at warmer temperatures. And so this formula, as you'll see, has a temperature correction coefficient. So cold water is less likely to form hydrogen sulfide than warm water is because bacteria are more active. And so the things that tend towards a high hydrogen sulfide potential would be a big wetted perimeter and a high BOD concentration. And the things that would tend towards a lower hydrogen sulfide concentration would be cooler temperatures, steeper slopes, because if you have a steep slope, then the water velocity is faster and there's more aeration and mixing of the liquid. So that's a little bit of background about hydrogen sulfide. Once you calculate the Z potential, then if you get below 5,000, typically under conditions like that, it would be uncommon for hydrogen sulfide to form. Above 10,000 and it's likely, and then in that middle ground it's possible. You know, it's not definitive. It may occur, it may not. But if there are things that you could do to calculate the Z potential and then adjust your design, then it's a good thing to have on your radar, is balancing out the fact that we want to make the pipes big enough so that many years in the future, all of the capacity is in the ground to accept the wastewater for all of the areas that are going to be developed. Remember that if this pipe is in the ground for 50 or 100 years, we want to make sure that the pipe is big enough to service all of those areas at the end of the useful life. But then on the flip side of it, in the early years where the flow rates are low, that pipe may be larger than we would prefer because it increases the formation of hydrogen sulfide. Okay, so here's another example. This combines both hydraulics and then also calculating the hydrogen sulfide risk. So let's say that we've got a pretty large concrete pipe here, 0.75 meters diameter concrete pipe. When concrete pipe is full, it has that N value of 0.013. It has to carry a flow of 0.92 cubic meters per second of wastewater. That's at 33 degrees Celsius, so it's warm wastewater, and it's laid out on a slope of 0.8%. So what we're going to do is together go through calculating the angle, and then using that to determine the wetted perimeter, top width, and depth that we'll need to put into this hydrogen sulfide potential formula. So we're going to use this top formula, Manning's equation. We're going to use Manning's equation to tell us what is the angle. And then once we know the angle, we'll use that to find out the wetted perimeter and top width. So let me write on the whiteboard the formula that we're going to put into Wolfram alpha. You could also do it on your calculator, solve the equation. Actually, let me just bring it up on the screen as well. Here it is. All right, so we've got a pipe that has a diameter of 0.75, temperature 33 Celsius. The slope is 0.8%. That means 0.008 because it needs to be written as a decimal into Manning's equation. The full end value is 0.013, and the flow rate is 0.92 cubic meters per second. So here is Manning's equation as we are going to put it into Wolfram alpha and then try and solve for theta in radians. So let me bring that up. Wolfram alpha, and then the equation that we're putting in as I'm doing that, why don't you see if you could get your solver to tell you what is theta? I'm not sure how quickly the numerical solver works on the Casio. Let's just give it a shot together in parallel. So theta to the negative 2/3 power times theta minus sine of theta to the 5/3 power minus 20.16 times the n value of 0.013 times the flow rate of 0.92 times the diameter 0.75 to the power of negative 8/3, and then times the slope of 0.008 to the power of negative 1/2 is equal to 0. And we want to know what is theta for that. Okay, so let's see if we can get Wolfram alpha to give us this one. So it is, I could use any variable, I guess, but I'll put it in terms of, where are they? Here it is, theta. Theta to the power of negative 2/3 times theta minus the sine of theta, and that to the power of 5/3 minus 20.16 times 0.013 times 0.92 times 0.75 to the power of negative 8/3 okay, times 0.008 to the power of negative 0.5, and then all of that is equal to 0. Anybody notice any obvious errors here? I think it's typed in okay. That's probably hard to see. All right. Okay, so let me just tell it to solve it and see what we get for the angle. Theta is 4.229 radians. That's what I previously got. 4.229 radians. Anybody get the Casio solver to give you that? Still going.
Go on about 30 seconds.
Well, hold it up to the light. Maybe it'll run faster if it's getting plenty of sun. It'll be interesting to see if it does converge eventually. But But that is the angle. So once we get the angle, let me show you the rest of what we're doing here. So knowing the angle allows us to find the wetted perimeter. So wetted perimeter is diameter times the angle divided by 2. Now radians is a weird unit. It's like actually unitless. Radians isn't really a unit. So like the wetted perimeter, we know that should have units of length. So 0.75 meters times 4.229 radians divided by 2. The result of that is just 1.586 meters. It's not meter radians, it's just meters. Same thing is true with the top width, B. We multiply the diameter times the sine of theta divided by 2. We get 0.642 meters. We don't, strictly speaking, need to know the depth, but I mean, you know, it's a curiosity, might as well. So the depth here is going to be 0.569 meters, but what we're really trying to do is estimate the probability that hydrogen sulfide is going to form. So let's first of all calculate the effective BOD. So it's the given BOD of 350 milligrams per liter multiplied by that temperature correction factor, 1.07 to the power of 13, because we're 13 degrees above 20 Celsius. So the BOD effective will be 843 milligrams per liter. And now we put all of that into the hydrogen sulfide potential formula, calculate Z. And this is suggesting that we're in that middle zone. 7373 is the hydrogen sulfide potential, and between 5,000 and 10,000 it may form. So, you know, this pipe is 0.75 meters in diameter, but it's only 0.57 meters in depth. So what we'd maybe want to ask is, could we make this pipe diameter smaller? Because if we made the pipe diameter smaller, everything's going to go in the better direction in terms of preventing hydrogen sulfide formation. That's the environmental part of it. Any questions about the hydraulics component of it? Did the Casio ever converge? Still going? You're going to need a new calculator. You've stumped it.
Oh, actually, it just gave me something. It just said can't solve.
Well, shoot. I wonder, with the Casio, do you have to give it an initial guess?
Yeah.
Okay, so I wonder if you gave it an initial guess if it would solve faster. Did yours solve?
No, it didn't. And
No.
I gave it an initial guess.
Yeah, I gave it an initial guess on that.
Shoot.
It was just too far.
Well,
I don't know if it was just too much for me.
Yeah, one of these days we're going to get stronger calculators. It won't be an issue anymore. All right, so we've got one more class. Remember that your assignment is due Friday before class. So let me know if you've got any questions on homework 13.